All right, in this video we are going to look at finding a basis for a couple of different planes in R3. So ultimately you want to be able to find a basis for whatever vector space you're given. But for right now, this video, we're going to just focus on planes in R3. So remember that a basis is a set with two important properties. One, it spans the vector space. And two, it is linearly independent. The other thing that we talked about is that your geometric sense of dimension should help you here when you think about a basis. Remember that dimension, in terms of a basis, is the number of vectors in any vector space, in any basis for the vector space. So the dimension is the number of vectors in a basis for the vector space. So when you think about a plane, a flat plane, thinking about that the plane has two dimensions. The plane might live in a higher dimensional space in R3. R3 is three-dimensional. But the plane itself is two-dimensional. The simplest plane might be like the XY plane in R3. XY plane is just two-dimensional. You can go in the X direction or the Y direction. But if you transform that plane and think about rotating it or moving it in R3, it's still a plane. And you still have an ability to go kind of one direction and another direction, two dimensions. So planes, you should have a geometric sense from way back in geometry, but then also when you worked in three-dimensional geometry, when you took multivariable calculus, thinking about a plane as two-dimensional. Even though the plane might live in three-dimensional space, the plane itself is two-dimensional. So that tells us that when we think about finding a basis for these spaces, our basis should have two objects in it, two vectors in it. All right, so my basis for this first vector space, I'm going to draw some little pictures here to think about this a little bit. I need to have a set of two objects. They need to be objects that are in the overlying vector space, so they're going to be vectors in R3. So my basis is going to be two vectors in R3. So I'm going to write those as 3x1 matrices. And you obviously don't have to write 3x1 here. I'm just writing that as a little reminder to myself of what I'm expecting to write down here. So I need two because that's the dimension. They need to be 3x1 vectors because they need to be vectors that are in this vector space, so with three entries. They need to be linearly independent, and they need to span this plane. So they need to be on the plane, and then also when I take all linear combinations of them, I get everything on the plane. We've looked at this specific plane in some previous examples. And I intentionally did that to try to help make this transition to think about basis a little bit more gentle, and then we'll look at something that we haven't looked at explicitly before. All right, so if I think geometrically about this plane, y equals 2x, the trace in the xy plane is the line y equals 2x, and then extends up and down parallel to the z-axis. All right, so there is our plane. You don't necessarily have to draw that, but the geometry can help you. As long as your geometric sense is good, you might as well use it. Right? So thinking about, I need vectors that are on this plane in order to generate that plane. And when I drew this plane, I drew it kind of by drawing really what I need for basis vectors. I started by drawing that trace in the xy plane. So this line in the xy plane. If I can write down a vector that generates that line in the xy plane, that generates part of what I need for the basis. Right? So just thinking about where that line came from. It's the line y equals 2x, but it's in the xy plane, so the z entry, the third component of that matrix, will be 0. But I need the y entry to be twice the x entry. All right, so I'm just going to write down a vector where the y entry is twice the x entry and the z direction is 0. Okay, so that is the vector 1, 2, 0. In a previous video, we looked at actually thinking about the span of a set, and we drew that vector as a vector. Right, so there's that vector, and then when I take all scalar multiples of that vector, I get everything along that line in the xy plane. That's what I drew first when I drew this plane, and then the next thing I drew was extending parallel to the z-axis. So if I just think about a vector that would allow me just to go up or down when I take scalar multiples of that, then I can get something in the z direction. So there are lots of choices you could make here. But the simplest choice is really just the vector 0, 0, 1. So when I take scalar multiples of that vector, I can go up or down in the z direction. All right, in a previous video, we looked at the span of this set of vectors and concluded that the span of this set of vectors is this plane. Right? So we're using some of that work and logic that we did before to think about why the span of this set of vectors is that plane. Here we're kind of thinking through it in the other direction, starting with the plane, wanting to write down some vectors that span that plane. So we've already kind of talked about that. The other thing that's important is thinking about linear independence. I need to ensure that this set is linearly independent. And again, if you've had linear algebra, you might know some theorems or shortcut ways to think about justifying that this set is linearly independent. But if you haven't already had linear algebra, just refer to the things we've already talked about in this class. You can use the definition of linear independence. Think about taking just generic scalar multiples of these vectors and adding them, so a generic linear combination of those vectors, setting that equal to the 0 vector, and determining if that system has more than one solution or not. Or we did talk about a shortcut. If you have a set with only 2 objects in it, only 2, this shortcut only works when you have 2 objects, but if you have a set with only 2 objects in it, it's relatively easy to tell that that set is linearly independent. All you really have to check is that one vector is not a scalar multiple of the other. It should be pretty obvious because of where I've put the zeros here that I cannot take one of these vectors and take a scalar multiple of it and get the other one, because any scalar times 0 would give you 0, not 1, 2, or 1. Right, so this set is linearly independent and it spans this space. There are many, many other bases you could give for this plane, but this is probably the simplest basis. The only other option maybe that you might think about is sometimes people like to have unit vectors in their basis. Back in Calc 3, you talked about how to rescale a vector to make it a unit vector, so you could certainly do that if you want. If you're taking linear algebra, you might also sometimes want to make sure you have orthogonal vectors in your basis. These ones happen to be orthogonal, but you might learn a process for forcing them to be orthogonal if they're not already. But this is a simple basis that we could use to generate this plane. There are infinitely many other answers that I could give, but they all need to generate the entire plane. They all need to be linearly independent, and any answer I give should have 2 vectors in it. All right, so that connected to a problem that we had looked at before. I want to kind of transition to one that we haven't looked at before. This is a plane, and it is in R3, but it's a different plane, not a specific one that we've looked at before. So you could think about geometrically drawing this plane, but the key is that it's a plane. It's a plane. It's 2-dimensional also. So my basis should contain 2 vectors. Dimension is number of vectors in any basis. So 2 vectors. This plane is in R3, so these are going to be 3x1 matrices. Right, so just kind of thinking through what I'm expecting to be able to write down. And then also sort of connecting back to what we did here, really what I found is two vectors that are on this plane. Algebraically, that means they satisfy this equation. Right? Algebraically, 1, 2, 0 satisfies this equation. Y is equal to 2 times x. And also algebraically, 0, 0, 1 satisfies this equation. 0 is equal to 2 times 0. All right, so algebraically, if the geometry isn't quite as obvious as it was in this first example, you can also leverage the algebraic expression that you have for your plane. I need two vectors that are on this plane, so satisfy this equation. So there's lots of different choices you could make. I'm going to be kind of strategic and choosing a couple zeros in a couple places here. So for example, if I choose y, if I choose y and z to both be 0, then that would force x to be 0, and it would have the 0 vector. Remember that no set containing the 0 vector is going to be linearly independent. So I don't want to choose two variables to be 0 because that would force the third one to be 0. Notice that's going to be true in all these. But I could choose one of the variables to be 0 and then easily choose some values that make the other two true. So if I choose z to be 0, and then think about choosing x and y that would satisfy this equation, you're going to have x plus y equals 0. I'm sorry, x plus 2y equals 0. Or x is equal to negative 2y, depending on how you want to think about that. Be careful and make sure that you choose values that actually do make this true. A lot of times I see students sort of gloss through this step and write down wrong numbers here. Like they'll just take coefficients and say x is 1 and y is negative 2, but that doesn't make this equation true. It does work if y is 1 and x is negative 2. So this is very easy to pick numbers that make this equation true. Just be careful and make sure whatever you pick actually does make it true. A lot of times see students get these numbers backwards. Right? So just verify. When I put in 1, then I get x equals negative 2. Okay, so now I need another vector that also is on this plane and is linearly independent from this one. So an easy way to ensure that it's going to be linearly independent is to use the zeros to your advantage here. I picked z to be 0, so that allowed me to pick x's and y's that made that equation true. I'm just going to pick another variable to be 0 and then choose others to make the equation true. So it doesn't really matter what I choose here. I'm just going to pick y to be 0. And then I need to pick x's and z's that will make this equation true. Or geometrically, that would mean the vector lies on this plane. So when I pick y as 0, I get x plus 3z equals 0. Or x is equal to negative 3z. Again, be careful. Make sure the numbers that you choose actually do make this true. But if z is 1, then x is negative 3. All right, so this is one possible basis for this plane. There are infinitely many other answers. It may not be obvious that what you write down and what I write down are both possible correct answers because they may not look exactly alike. But I would need to make sure I have two of them because of the dimension. They are linearly independent. So you can either use the definition to check that, or if you only have two objects, it's easy to tell that they are or are not scalar multiples of each other, and that they span that plane. So thinking about taking all linear combinations of these, and do you get everything on this plane? If you have the right number of linearly independent vectors, then it will span that set. That's one of the properties of vector spaces or basis that we looked at in our class notes. So that's an advantageous thing to being able to think about the dimension. If the right number of linearly independent vectors, so they should span this plane. You can look at the definition of span and analyze that as well. But for our purposes in this class, we really just want to be able to think about what we're working with and write down a basis. So we probably won't generally go through that whole definition. We'll use understanding how many I need, ensuring that they're linearly independent, And then it should follow that if I've thought about those two things correctly, the span should follow from that. All right, try some other problems with not only vectors, but other sets that we have worked with in this class. This is a lot of content to pull together, so it's okay if you're struggling a little bit with it as you work on it, but keep at it and it'll all come together, I promise. All right, thanks.